Hi all, this talk is going to be about what are called self-normalized concentration inequalities, and these are again this is a method to prove concentration inequalities for functions of sequential processes where current random variables depend on previous random variables, and so there's a lot of time correlation. So let's introduce the necessity for these kinds of concentration inequalities in the context of a motivating example involving estimation, parametric estimation. Okay, so what's the arguably simplest kind of parametric estimation problem? Well, it's often a regression problem. So let's consider a standard. Let's start off considering a standard least squares regression problem, a linear regression problem, in what we call the fixed design setting. Okay, so what is the fixed design setting? You have n d-dimensional vectors x1, x2 up to xn. These are fixed or non-random vectors, also called your design. Okay, so these are essentially vectors that represent your choice, the experimenter or data collector's choice of directions to measure upfront. So the design vectors x1 through xn are fixed upfront. Let theta be a d-dimensional unknown parameter, and let yi be a random variable which is the inner product of xi with theta with an additive Gaussian noise, independent Gaussian noise variable wi, which has mean 0 and standard deviation sigma. And the goal is, as usual, we want to recover or estimate theta from our data xi yi. Okay, so this is the standard regression problem with Gaussian noise, additive Gaussian noise, and the most natural way to estimate theta is what is called least squares regression or linear least squares estimation. So the linear least squares estimation is solving the following optimization problem. So the estimate for theta from these n data is defined to be theta n hat, which is the solution to a minimization problem over all possible theta tilde in Rd of the sum over your data of the fitting error. So xi transpose theta tilde minus yi, and if the xi's are chosen, let's say, so that they span the entire space Rd, then it's not difficult to show that this has an explicit closed form solution as sum over I going from 1 to n xi transpose. So this is a matrix inverse. So if the xi's all span theta, then this matrix is going to be full ranks and hence invertible into this particular vector, which is the weighted sum of the xi's with the respective scalar measurements yi. Okay, so this is true if so let's denote this matrix whose inverse is being taken as Vn. So this is true if Vn is invertible or equivalently full rank. Okay, so this is the standard linear least squares estimate for inference about the unknown parameter theta of this linear model. And in fact, it turns out that since we have assumed that the xi's are all fixed, the Vn is a fixed or non-random matrix. So theta hat n is just a fixed linear function of the sequence of Gaussian random variables y1 through yn, and it follows that since all the random variables y1 through yn are multivariate normal together, it follows that theta hat n is also the estimate theta hat n also has a multivariate normal distribution. So more precisely, it follows that theta hat n is distributed as a multivariate normal vector with mean as the original parameter theta, and with covariance matrix sigma square Vn inverse. So sigma square, recall, is the variance of the per measurement additive noise, and Vn in some sense is the overall design matrix representing how much of each direction in space of d dimensions, how much is being explored. So if we just do some linear algebra, it follows that 1 over sigma into the square root of Vn into the difference theta hat n minus theta is distributed as a standard multivariate normal vector. Okay, this is the left hand side is in some sense just the whitened form of theta hat n minus theta, and this in turn implies, by using standard concentration results for multivariate normal vectors, that the probability that the L2 norm of this vector 1 over sigma square root Vn theta hat n minus theta, okay, which is basically the L2 norm of a standard multivariate normal in d dimensions, exceeds let us say some constant times the square root of dimension plus another constant times square root of log 1 by delta, is bounded by delta. Okay, this is just by appealing to standard Gaussian concentration. Since the L2 norm function is a Lipschitz function with respect to the L2 norm itself, and so you can use the Gaussian concentration inequality along with basically this C1 square root t, which is actually a bound on the expected value of the L2 norm of a standard Gaussian vector. Okay, so that's where you get this from. So the second term here comes from concentration about the mean. The first term is basically by estimating the expected norm of a Gaussian vector itself. Okay, so this is standard. So we basically get this kind of concentration inequality for the fluctuation of theta hat n about theta with respect to the shape Vn as well. Let's denote. So denoting by x subscript a, the square root of x transpose ax. So when when A is a positive definite matrix, this is often called the matrix weighted Euclidean norm. Okay, so if A is the identity matrix, then you get the standard Euclidean norm. So the above suggests that, so if you define this particular d-dimensional subset Cn as the set of all beta d-dimensional vectors such that the L2 norm of 1 over sigma Vn raised to half theta hat n minus beta in L2 norm is less than C1 square root d plus C2 square root log 1 by delta. So notice that this can equivalently be written by rescaling as the set of all betas such that theta hat n minus beta. So the L2 norm of v raised to half theta hat n minus beta is equivalent to the Vn matrix weighted norm of theta hat n minus beta by definition, being less than C1, so you can multiply throughout by sigma. So this set, so based on your data, you could compute theta n hat and you could also compute Vn. In fact, Vn is known in advance even before collecting the measurements y1 through yn, because it's a fixed design setting. But in any case, this set Cn, which is basically an ellipsoidal set in d-dimensional space, is actually a probability 1 minus delta. So what we get from the concentration inequality above is that this particular set Cn is a probability 1 minus delta confidence set. In fact, it's an ellipsoidal confidence. You can call it a confidence ellipsoid specifically for the true parameter theta of the linear model. Okay. Okay. In the sense that the sense of the confidence set is that probability that theta belongs to Cn is at least 1 minus delta. Okay, so if you had this data x1, y1 up to xn, yn, and if you constructed this set Cn, you can be assured that Cn is a high probability confidence set that will typically contain theta within it. Okay. So we now next come to a more complicated setting which often arises in practice, and this is the setting of not fixed design linear regression but adaptive design linear regression. It's also called online linear regression, but the setting is basically as follows. Suppose the measurements xi are also random along with the yi's, in the sense that suppose the xi are chosen sequentially and adaptively depending on the previous x's and y's. Okay, so by that what I mean is as follows. So there is this dependency diagram that we can imagine. So x1 is the first linear measurement, the first direction along which you want to collect a noisy projection of the unknown parameter theta. So you choose x1, let's say using some internal randomness, and then you apply x1 and you get the first measurement as y1, which is x transpose theta plus w1. Okay, so this arrow indicates that y1 depends on x1 via this function. Y1 is exactly x1 transpose theta plus w1. Followed by this, x2 is chosen, but x2 can depend on y1 and x1. So that's why x2 has arrows coming in from x1 as well as y1. This arrow is redundant. Okay, so x2 can depend on x1 and y1, following which y2 is obtained only depending on x2, following the linear model x2 transpose theta plus w2. Following y2, x3 is a new direction that can be computed by looking at all the past data. So x1, y1, x2 and y2 can be used to decide x3, and so on and so forth. Okay, so the key difference from the previous fixed design setting is that the future linear measurements, that is the xi's, can actually depend on the outcomes seen so far. So upfront there is no way to predict or decide what the trajectory of the measurements xi's will be as opposed to the fixed design linear regression setting. So both the x's and the y's are random here in this sequential or causal manner. Okay. So that's what is called adaptive design linear regression. It often arises in settings where the next measurement is designed or constructed carefully by looking at the history of past measurements. Okay. When there is the ability to adapt your next sensing decision or measurement decision based on whatever has happened in the past so far. So in this more general case, it's actually not too hard to see that in fact theta hat n, which was multivariate Gaussian earlier in the fixed design setting, need not be Gaussian anymore. Its distribution as a vector in d dimensions need not be Gaussian in the general case. There are examples where it can be quite far away from the Gaussian distribution in the sense of having tails and so on for certain kinds of measurement processes. Moreover, theta hat n in general can even be a biased estimate. So in the fixed design setting, note that the expected value of theta hat n was theta, because theta hat n was a multivariate normal centered at theta. But in the adaptive design setting, there could be biases because of the data collection mechanism or the measurement mechanism that decides the next xt depending on the past, which could actually introduce a bias in theta hat n. Okay, so expected value of theta hat n. So when I say the expectation, this is over the randomness or distribution of both the x's and the y's. Okay, this expectation need not be equal to theta anymore. Okay, but the question still remains. The interesting question from an inference point of view still remains that is it still possible to build or construct a high probability confidence set for such an adaptively constructed estimate theta at n after n adaptive measurements and at any point in time small n. Okay. Okay, note that even if you are at a fixed point in time small n, the pattern of taking measurements x1, x2 up to xn could have a general distribution and be random. So one has to worry about that aspect as well. Okay, so the same Gaussian theory doesn't hold because essentially your theta hat n, which is Vn inverse into summation yi xi, is such that both the Vn part and the yi and the xi's are all random. So it's simply not a fixed linear transformation of a sequence of Gaussian random variables and so on. So is there any hope? Is it still possible to build in some sense analogous high probability confidence sets for adaptive estimates, adaptive sequential estimates? And the answer is rather surprisingly yes. In fact, one can argue, we will argue now that an ellipsoidal set, confidence set, very similar to the fixed design confidence set that we call Cn, let's say in this equation star, Cn of star can be constructed. But of course we have to pay a price for being adaptive and incurring some bias, so there will be some inflation that we'll have to do. To handle the extra bias as the, so at a high level this is the price of being adaptive over time. So we'll see exactly how much of a price we will have to pay. And so this is where the idea of concentration inequalities for adaptively constructed estimates arises via what is called self-normalizing inequalities, self-normalized inequalities. So just to set the stage, recall that in the adaptive linear regression setting, the next measurement xt can depend on is some function of the past measurements and sensing actions, that is the y's and the x's in the past. So let's start by rewriting theta hat n in a slightly different form. So recall that theta hat n was defined as the summation of I equal to 1 to n xi transpose inverse into the sum of xi yi. Note that the xi's are now in capital letters because they can be random in the adaptive setting. So we'll still use, we'll still call this as Vn. However, Vn is a random matrix now. So we can write this as Vn inverse, and by definition, we can expand yi as xi transpose theta plus wi, because that's the assumed linear model for the yi's. So the WIs are IID, normal, 0, 1. Let's say let's assume we normalize the variance of the noise to 1 in whatever follows, and so this is equal to Vn inverse. If you expand, if you distribute the inner sum, you get a Vn times theta by definition, plus the second sum, which is Wi xi. Let's call this sum as Sn. Okay, and so this finally gives you theta plus Vn inverse Sn. Okay, so theta hat n is exactly equal to the original theta plus Vn inverse Sn. Theta is the original non-random parameter. Vn inverse Sn is a random vector which could have bias because of adaptive data collection. Nevertheless, if we take theta to the other side and find the Vn norm, okay, the Vn weighted matrix norm of theta hat minus theta, then we just get the Vn weighted matrix norm of this Vn inverse Sn. Okay, this by definition is Sn transpose Vn inverse followed by the Vn in between and then again Vn inverse Sn. And so this and this can cancel. So you finally get, so it's equivalent to a certain inverse matrix mated norm of this quantity Sn. Okay. Now the important, so if we want to control theta hat minus theta, let's say in the Vn norm as before, as with the fixed design setting, this is equivalent to controlling the Vn inverse weighted norm of the random vector Sn. Okay, Sn itself is the sum of n random vectors, each of them being the Wi xis. Now, one thing that's worth noticing here is that both Sn and Vn in the adaptive design setting are random quantities. The former a random matrix and the latter a random vector. The former a random vector and the latter a random matrix. But we notice that there is a kind of self normalization. Okay, the self normalization essentially is that what is the what do we mean by self normalization? Sn grows, let's say basically linearly. This is very roughly linearly with n, because each time Sn grows by the addition of a new component Wi xi. Okay, and on the other hand, Vn grows again linearly with n. So linearly is in quotes because these are all rough statements, and hence Vn inverse grows, decays as 1 over n roughly. Okay, so Sn grows linearly with n, Vn also grows linearly with n roughly, and so essentially you expect Sn Sn normalized by Vn inverse or Sn normalized by Vn to be essentially of some kind of constant scale. Okay, there's a self normalization, so we can very roughly expect Sn Vn inverse to be of constant size. Okay, put differently, sort of, Sn can grow large, but so will Vn. Okay, so Sn normalized by Vn inverse can probably be expected to not become too large. Okay, just as with the fixed design estimate, estimate. So in the fixed design setting, things were a little easier because Vn was a fixed matrix. It was not random, so it was easy to handle terms involving Vn. So how is this? So how do we make this formal? Okay, so here's a result that we will prove for the adaptive, for concentration of the adaptive regression estimate uh, using a new technique which we will call the method of mixture. So this theorem is essentially inspired by the paper of Abbasi Yadkori et al. It's a paper about linear multi-arm bandits from 2011, which essentially establishes the following type of result. So let's fix some small epsilon. This is a constant. You should think of epsilon as a constant, and let delta belong to 0, 1. The probability, so this theorem says that the probability when the xi's are adaptively designed, that there exists any time t in the set of all natural numbers at which, so it's a uniform deviation statement for the entire self normalized process, st normalized by, so we add a small epsilon I plus vt. Okay, so the small epsilon I is sort of required because of the, so it enters through the method of proof. But imagine epsilon I has to be so small to not significantly affect the scale of Vt. So epsilon I plus Vt inverse is really roughly like Vt inverse. Exceeding a level 2 log 1 by delta plus this term, which is a log the determinant of this matrix epsilon I plus Vt divided by epsilon raised to d is at most delta. Okay, so this is what it says: the probability that at any time the self normalized quantity st inverse weighted by Vt square exceeds this particular number is bounded. Okay, so to get a sense of the scale of this number, so if delta is fixed, this is basically an order 1 quantity, and if delta is fixed, this is, you can show that this is roughly an order d log t quantity. So this is not too far from the kind of threshold self normalized level in the fixed design case, where you again had a order square root d term. So note that here the norm is not being squared, so you should imagine each of these terms being squared to make a fair comparison. So order square root d would be order d if you squared it, and this term is order square root log 1 by delta. Okay, so the order square root log 1 by delta squared would appear here as the log 1 by delta term, which is the order 1 term, except that we are paying a small price of this extra log t, okay, to be uniform in time. Okay, so this is the price of sort of, this is sort of in some sense the price of being able to uniformly control an adaptively obtained estimate, a function of a stochastic process. And you could think of this as not too large a price to pay. Okay, so it just scales logarithmically with the number of time steps here. Okay, so but for a small blow up, you get exactly uniform deviations. So let's see how this kind of result is obtained, and the proof is going to expose a very interesting technique called the method of mixtures. So this is called the method of mixtures for martingale processes, which is probably the most interesting takeaway from this lecture that I'd like you to have. Okay, it's also related very intimately to something called Laplace's method. So this was actually developed by Laplace uh, centuries ago, and used in modern probability theory by first by Robbins and Siegmund. Dates back to Robbins and Siegmund in 1970, and there's a survey book by De La Peña of 2008, which actually details a lot of applications of the method of mixtures technique. Okay, so what is the method of mixtures technique? So we note first, let's start by noting the following, that if you, so the quantity that whose fluctuations we want to control uniformly in time is equivalently the ST, the norm, the VT inverse norm of this random walk type object ST. Okay, so half of VT inverse norm of ST squared. In fact, you can show just by linear algebra that this is the solution to the following variational problem. It's the solution to max over lambda in RD of lambda transpose ST minus half the VT norm square of lambda. Okay, so this is actually an identity that expresses actually a matrix weighted norm as the solution to an optimization problem involving the weighted norm of the inverse matrix on the other side. Okay, so VT inverse becomes VT on the other side. Okay, so so if we transfer our attention to the right hand side here, we would like to control the left hand side. So equivalently, it makes sense to try and control so one sufficient way to do control the left hand side is to be able to control this particular quantity here for every possible value of lambda. Okay, thus leading to an upper bound on the left hand side. Okay, so towards this is sort of what brings us to the Laplace method or the method of mixtures. So to this end, for every vector lambda, let's define the following quantity. Define empty lambda. This is a random variable, which is e raised to lambda transpose st minus half the Vt norm square of lambda. Okay. Right. So this empty lambda, if you think of lambda as fixed and t evolving in time, it forms a stochastic process m1 lambda, m2 lambda, m3 lambda, and so on. And this is the key claim that makes that allows us to do something useful with this process. It turns out that the sequence of random variables empty lambda as t goes from 0 to infinity. By the way, if t is 0, this is an empty sum, and so you just directly get m0 lambda is defined to be 1 trivial. So in fact, this process over time for a fixed lambda turns out to be a martingale. Okay. More specifically, what we mean by this is that for any time greater than or equal to 1, if you take the conditional expectation of empty lambda given x1, y1, all the previous measurements, and all the previous sensing decisions and the observed measurements, then this is equal to mt minus 1 lambda almost surely. Okay, so what is the proof of this claim? Well, it is the fact that the left hand side, so in fact we note that because of the adaptive sensing, xt is already determined once x1, y1 and all the way up to xt minus 1, yt minus 1 are given. Okay, so if you have this conditional expectation, empty lambda is the e raised to lambda transpose a sum minus another sum. So the left hand side of the expression above, in the left hand side you can actually bring out the second term here, you can bring out the term here corresponding to to xt in fact. So that's the e raised to minus half lambda transpose xt the whole square. This is just the last term in norm lambda vt the whole square. It comes out because xt is already measurable with respect to x1 y1 up to xt minus 1 yt minus 1, just because of the causal nature of the sensing decision xt. And then you have mt minus 1 lambda that also comes out of the conditional expectation, because it's a function of exactly all these things, x1 y1 up to xt minus 1 yt minus 1. And the only thing that remains inside the conditional expectation is the first term, is the last term of lambda transpose st, which is basically e raised to wt lambda transpose xt given everything in the past. And given everything in the past, the only randomness is in this wt random variable, which is an independent standard Gaussian by assumption, whose moment generating function is precisely, so you have all of these terms, and the last term, the conditional expectation, is exactly the moment generating function of wt evaluated at this inner product lambda transpose xt. And so you just directly get, this is the moment generating function of a Gaussian, half lambda transpose xt the whole square. Okay, so the first term and the third term cancel, leaving you with what you require. Okay, so this is because wi are assumed to be IID standard normal. Okay, so what does this show? For each fixed lambda, empty lambda is actually a martingale process, in the sense that it essentially doesn't change its mean on an average. So hence e raised to the quantity that we want to control, which is half st vt inverse square, is actually exactly equal to the supremum of a martingale at time t, of an uncountably large collection of martingales. Okay, so empty lambda we have just shown is a martingale for a fixed value of lambda, and in some sense, what we want to control is on the left hand side, up to a monotonic transformation of e exponentiating, and we essentially would like to control the fluctuations of a supremum of many martingales. Okay, so unfortunately, this supremum of many martingales. So we know very well there is a lot of martingale theory that tells us about the fluctuations of martingales, results like Azuma's inequality for martingales and so on. But the maximum of many martingales is unfortunately not in general a martingale. So we cannot control this right hand side. So we cannot control this supremum over many martingales using standard results like let's say Azuma's inequality or its variance. Okay, so this leaves us with sort of this, we're at this brick wall where we haven't, we can't really proceed at first glance to control this supremum of a really large family of martingales. So this is exactly where the method of mixtures enters and helps us find a way forward, or also called, so you can really view it as an instance of what is called the Laplace integral approximation. Okay, so what is this Laplace integral approximation or Laplace integral formula. So suppose it's sort of this following phenomenon. Suppose f is a function. You can say f is let's say a smooth function on defined on the interval a cross b. Okay, so it's a real to real function with a maximum at an interior point lambda star in AB. Okay, so f accepts an argument lambda in the interval AB, in the closed interval AB, and its maximum actually occurs at its interior, somewhere in its interior. So so what one can show using basically Taylor approximations up to second order is the following. So if you integrate the function e raised to s, so fix s as some real number, a large real number, e raised to s f lambda d lambda. Okay, so consider integrating e raised to s f lambda over the integral over the range a to b. As s becomes larger and larger, one can argue that this essentially tends to e raised to so basically you recover e raised to s times the value at its maximum point into square root 2 pi by s times some constant, where this constant depends essentially on the smoothness of, uh, of the function f. About its maximum point lambda star. It's essentially like uh, it relates to the Hessian of or the second derivative of f at lambda star. So the point of this is up to a constant, you essentially by integrating you recover e raised to the maximum value. Okay, so the implication here is that the key implication here is that maximization is roughly equal to approximate integration. Okay, so the integral is a convenient approximate way to find the maximum, okay, in some sense. And this is very useful in our context because we can consider, instead of the sup over lambda of empty lambda, what we can do is we can set up the stochastic process mt, we'll define this as mt, as the expected value over lambda drawn from some distribution q over Rd of empty lambda. Okay, so think of so this is essentially, you know, what this is doing is basically integrating or mixing across martingales empty, and the convenient fact here is that this is actually a martingale itself because it's the average of a bunch of martingales. Okay, so it retains the martingale property for any probability distribution q on Rd. Okay, so no matter how many martingales, even an uncountable family of martingales you average, you will still get a martingale. Okay, and since this is a martingale, its fluctuations are very easy to control using standard martingale results, and indirectly we can also get a handle on controlling its supremum, which is what we seek to control finally. Okay, so this is the high level idea, and the details will be spelled out shortly of how this helps. So let me just put down this claim that the mixture of all these empty lambdas, where lambda is independently chosen as a vector from some convenient distribution Q over Rd, forms a martingale. With respect to the same filtration as we had earlier with respect to x1, y1, x2, y2 and so on in the same way. Okay, so this is something that you can easily check offline. Okay, and in fact the beauty here is that for a convenient choice of the distribution Q, the measure Q, there is actually an explicit closed form solution for closed form expression for MT. MT is expressible in closed form thanks to properties of the Gaussian measure. Okay, so this is remarkable. So to show this, let us define for any positive definite matrix P, C of P as square root 2 pi to the D. So P is a D by D positive definite matrix divided by the determinant of P. So this is also equivalent to integral of e raised to minus half x transpose Px over Rd for any positive definite matrix P D by D. Okay, so recall, so let's choose, in fact, so let's take the distribution of the distribution Q again as a standard normal. Let's say with the mean vector 0 and covariance matrix some epsilon times identity. Okay, where epsilon is some is this epsilon greater than 0 number. So think of it epsilon as basically a small number. Okay. So with this what we have is that we can explicitly start writing MT as the integral of MT lambda. So e raised to, this is MT lambda here, e raised to lambda transpose ST minus half lambda Vt square with respect to the density of the Q distribution. So F lambda is a notation for the density of the Q measure, which is the multivariate normal with covariance epsilon I. And after some straightforward linear algebra, which you can verify, you can show that this is actually exactly equal to the C of epsilon I plus Vt divided by C of epsilon I into, remarkably, e raised to half St square epsilon I plus Vt inverse. Okay, so this is exactly, so this exactly turns out to be an explicit function of what we actually wanted to control in the first place, which is this St inverse weighted by norm Vt inverse with some extra term in the front, and this extra term is precisely the determinant of epsilon I by definition, which is epsilon to the d divided by the determinant of epsilon I plus Vt whole raised to half into e raised to half the weighted norm of St, the self normalized term here. Okay, and this is basically a martingale. Okay, to finish the proof of the result, we will appeal to a standard result in martingale theory, which we will not prove during this course. You can go and look up the proof separately. So this is called Dub's inequality for Dub's maximal inequality for martingales. So it's a very well known and it's elementary but a very powerful inequality. So it says basically that if you have a non-negative martingale, so MT as above actually satisfies this property. If MT over all time is a non-negative martingale, then the probability that its maximum over t going from 1 to n, so let me just write this precisely as t belonging to n, mt exceeding any level epsilon is at most 1 over epsilon into expected value of m1. This is very similar to Markov's inequality, except that it strengthens it by allowing you to replace max, the supremum of this martingale over an interval of time 1 through n, by actually replace it with its first element m1. Okay, so that's what Doobe's maximal inequality allows you to do. So applying Doobe's inequality, we get that for any natural number n, the probability that the max over t less than equal to n of log mt exceeding log 1 by delta. Okay, so you can just exponentiate both sides and then you will get 1 over 1 over delta into expected value of m1, which is 1. So you finally get delta. And so this means that you can just turn this around to say that the probability that there exists t less than equal to n, for which, so you can sort of replace, you can substitute for log mt, and you will get the probability that the inverse weighted norm of st exceeds twice log 1 by delta plus log the determinant of epsilon I plus Vt by epsilon to the d. So this is so you basically get the same thing as you get this is the same expression here is at most delta. Okay, and so there's only one last thing remaining, which is a technical improvement. So there's nothing here in this part which depends on the n here. So this n is just any convenient n. So you can let actually n tend to infinity. So you can replace infinity, which is a technical procedure that we will not concern ourselves with in this class. But it suffices to say that this n is really a placeholder n. It can be as large as you want, because the rest of the property here really has nothing to do with this finite number n. So you can actually take this n all the way to infinity, okay, by a limiting argument, and that's what gives you the result that you get this sort of order 1 term or order log 1 by delta term, and you get sort of this order d log t term as a uniform fluctuation for the self normalized quantity st matrix weighted norm with epsilon I plus Vt the whole inverse, which is roughly a Vt inverse normalization of st. And that concludes this lecture. Thank you.